Okay, so today we are going to talk about Gay-Lussac's law and the combined gas law. So you've already learned about Boyle's law and Charles' law. And with Gay-Lussac's law, it just states that the pressure of the gas is going to be proportional to the temperature of that gas if your volume is constant. So with Gay-Lussac's law, the only variables that will change will be your temperature of your system and your pressure. So based off of the concept of Gay-Lussac's law, is that higher temperatures particles are going to have greater kinetic energy, so they're going to be moving faster. And because these particles are moving faster, they're more likely to collide with one another. They're going to collide with the walls of the container and also with each other. And by doing that, that is going to increase the pressure. So you can kind of think of it as if you have a bunch of people in a room and they're just walking around the room, it's very easy for them to avoid each other. But if they start to run, then it's more likely that they're going to run into each other or run into the walls of the room because they're moving so fast. So the same thing happens with particles in a gas. So when you heat up the particles of the gas, those particles move faster, and because they move faster, they're going to collide with the sides of the wall, which then in turn increases the pressure within that system. So this is just a graphical depiction of what happens in Gay-Lussac's law. So we have temperature versus pressure, and we see they are directly proportional to one another. So by directly proportional, that means that as one increases, so does the other. So as our temperature increases, we see that our pressure is also increasing. So just remember that this is the direction. So this is the graph that depicts Gay-Lussac's law. So the equation for Gay-Lussac's law is P1 over T1 equals P2 over T2. And like I mentioned in the previous videos, Gay-Lussac's law, the equation will not be given to you on the final exam. So it's important that you remember this formula. I will show you later how a trick so you don't have to memorize it, but for right now, this is the formula for Gay-Lussac's law. So if the volume remains constant, the equation you use is P1 over T1 equals P2 over T2. So let's do a practice problem. So what is the pressure inside a 0.25 liter can of deodorant? It starts at 25 degrees Celsius and 1.2 atmospheres if the temperature is raised to 100 degrees Celsius. And in this case, the volume is going to remain constant. So the very first thing you want to do is you want to make sure all of the pressure units match. And by that I mean, previously I showed you that there are 4 different units for pressure. You have atmosphere, millimeter of mercury, torr, and kilopascals. So you just want to make sure that all the pressures in that problem are in the same units. So when we look at our problem, we see that only one pressure unit exists. So we only have the 1.2 atmosphere. So since there's only one time that pressure is mentioned in this problem, then we're good. So we can move on to the next step. The next thing you want to do is you want to make sure that you convert all of your degrees Celsius into Kelvin. So remember, when we're dealing with gas laws, anything in this unit, temperature always has to be in Kelvin. So in order to do that, remember, so you have to add 273 to your degrees Celsius. So our initial temperature is 25 degrees Celsius. So we need to convert that to Kelvin. So we have 25 degrees Celsius. Oops, sorry. It's supposed to be 25 right there. But so 25 plus 273, that's going to give us 298 Kelvin. So that is our initial temperature. Our initial temperature is 298. And then we see that the temperature is then raised to 100 degrees Celsius. So let's go ahead and convert 100 degrees Celsius into Kelvin. So again, we'll take, didn't pop up again. So then we'll take 100 degrees Celsius plus 273. So that's going to give us our final temperature as being 373 Kelvin. So we have our initial pressure, we have our initial temperature, and we have our final temperature. So now let's go ahead and plug and chug. So these are everything that we know. Take inventory of what we know. So our initial pressure is 1.2 atmospheres. Our initial temperature is 298 Kelvin. Our final pressure is what we're trying to figure out. We don't know that. Our final temperature is 373. And remember, the equation that we're using, because volume is remaining constant, is P1 over T1 equals P2 over T2. So when we plug in all of these variables, you should get that your final pressure is 1.5 atmospheres. Now, here's another one that I want you to do on your own. You may want to pause the video right here. So you have a can of deodorant that starts at 43 degrees Celsius and 1.2 atmospheres. If the volume remains constant, what temperature will the can have a pressure of 2.2 atmospheres? So pause for a second, work this out. So you should get that you have to convert this temperature into Kelvin. So 43 degrees Celsius is going to be 316 Kelvin. And you're using that formula P1 over T1 equals P2 over T2. You're solving for T2, so you should get your T2 is 579, or you may have 580 Kelvin. It all just depends on how you round it. Either one of those is acceptable for me. So let's move on to another one. A can of shaving cream starts at 25 degrees Celsius and 1.3 atmospheres. If the temperature increases to 37 degrees Celsius and the volume remains constant, what is the pressure of the can? So in this case, we are solving for P2. So we have to convert our temperatures into Kelvin. So 25 is going to become 298. 37 is going to become 310. Oh, I meant to say pause the video here and go ahead and figure it out and then come back. So when you plug everything into that same equation, P1 over T1 equals P2 over T2, you get that your P2 is 1.35 atmospheres. And if you're struggling on how to rearrange these equations to solve for certain variables, just make sure you reach out to me and I will be more than happy to walk you through so you can actually see the process. But right now I'm just moving along. So problem 10, a 12-ounce can of a soft drinks at standard temperature and pressure. Remember, that's what STP stands for. So if you've forgotten what standard temperature and pressure is, you can always refer back to that first page on your reference table where it gives you all of the properties of, it will tell you what the temperature of a gas is at standard temperature and pressure and what is the pressure of a gas at standard temperature and pressure. So if the volume stays constant, at what temperature will the can have a pressure of 2.2 atmospheres? So you actually have a lot more information than you think from this problem. So just pause it right here and then come back. So you'll get that your T2 is 601 Kelvin. So I just wanted to point out, by telling you that you originally have a 12-ounce can of a soft drink at standard temperature and pressure. So this right here is all of your initial measurements. So you know that the standard temperature is 273 Kelvin and your standard pressure, because your final pressure is given to you in atmosphere, I would suggest you use your initial pressure in atmospheres. So standard pressure in atmosphere is 1 atmosphere. So those are your starting conditions, with your T1 being 273 and your P1 being 1 atmosphere. And then your P2 was 2.2 atmospheres. So when you rearrange that equation of P1 over T1 equals P2 over T2, you'll get that your T2 is 601 Kelvin. So now, that's all for Gay-Lussac's law. Now we're going to move on to the combined gas law. And the combined gas law is really interesting because it is the law that well, is exactly what it says. It combines all three of those laws. So we're combining the concepts of Boyle's law, Charles' law, and Gay-Lussac's law. So in this law, nothing is constant. You are changing all three variables. You are changing pressure, volume, and temperature. And this is the equation for the combined gas law, where it's P1 times V1 over T1 equals P2 times V2 over T2. And the thing with this one is you do not have to memorize the combined gas law. It is actually provided to you on your reference table. And I'm just going to show you real quick where it is located on your reference table. So if you go to the third page of your reference table, you'll see a formula list. And the combined gas law is the third formula down. So right here, this is your combined gas law. So you do not have to memorize this. And when we meet in class, I will show you how you can use this formula to actually generate Boyle's law, Charles' law, and Gay-Lussac's law. So back to our presentation. So now let's do a little bit of practice using that same formula. So we have a 15-liter cylinder of gas at 4.8 atmosphere, and at 25 degrees Celsius, it is heated to 75 degrees Celsius and compressed to 17 atmospheres. So what is the new volume? So let's look at what we have here. So the very first thing we have to do is we need to make sure that our volume units match. So volume, typically in chemistry, volume is going to be given to you in liters and sometimes milliliters. So you want to make sure they're all in the same units. So we have a 15-liter cylinder. Well, that's the only volume that's provided to us in this problem, so we're good. 15 liters, we're good. So now we need to make sure that our pressures match. So our initial pressure is 4.8 atmospheres and our final pressure is 17 atmospheres. So since they're both in atmospheres, we're good because they match. Now remember, if one was in atmospheres and one was in millimeters of mercury, you would have to convert to make them the same units. But in this case, we don't have to, we're fine. Now, because we're dealing with gas laws, we have to convert our degrees Celsius to Kelvin. So the very first one is 25 degrees Celsius. So to convert that to Kelvin, we are going to add 273 to that. So that's going to give us 298 Kelvin. So our initial temperature is 298 Kelvin. And so our final temperature is 75 degrees Celsius. So to convert that to Kelvin, we add 273 and we get 348 Kelvin. So that is our final temperature. So the question is, well, what is the new volume? So we have our initial temperature, we have our initial volume, our initial pressure, our initial temperature, and we have our final temperature and our final pressure, and we're trying to find our final volume. So let's go ahead and plug in our variables. So our P1, sorry, there we go. So our P1 is 4.8 atmospheres. Our V1 is 15 liters. Remember, 1 is always your initial stuff. Your T1 is 298 Kelvin. So now let's move on to plugging in our final conditions. So our final pressure is 17 atmospheres. And our final volume, our final temperature is 348. So we do not know what our V2 is yet. That is what we are solving for. So you rearrange this equation, however you want to do it, to solve for V2. So you'll get that your V2 is 4.9 liters. And I find that some students rearrange equations differently than I do. So if these two steps are different for you, that's perfectly okay. You may want to pause it. If you're kind of confused and you didn't get 4.9, you may want to pause it to kind of see what I did. But If you didn't do it this way, you still got 4.9, then you're fine. So all that matters is we get the same answer. Now let's look at our final example. I think it's the final one, where we have a 6.2 liters of gas at 723 millimeters of mercury at 21 degrees Celsius is compressed to 2.2 liters at 4,117 millimeters of mercury. What is the temperature of that gas? So once again, you want to convert your, So you want to convert your temperature into Kelvin. You also want to make sure that your liters are the same. That your volume units are the same. So our initial volume is in liters and our final volume is in liters. So we're good to go. There's only one pressure reading, so we're fine with that. So we convert our temperature into Kelvin. And using the combined gas law, you should get that your final temperature is 594, or you may get 590, just all depends on how you round. So if you didn't get that, make sure you ask that question in class. And that is it for the combined gas law and Guy-Lussac. So make sure you work on the practice problems in the Google document and bring all your questions to class, and I will see you guys later.